Hello everyone, I'm Shubham Chaudhary, presenting our work on balancing efficiency and fairness in heterogeneous GPU clusters for deep learning. This work was done in collaboration with my colleagues at Microsoft Research India. Deep learning has emerged as an important workload in today's compute landscape. It's used in all sorts of products with applications ranging from visual perception to machine translation. Companies deploy clusters of thousands of GPUs and models take days to train. Meanwhile, domain-specific system support in production DL schedulers is still very limited. Here is a summary of the state of the art in cluster scheduling for deep learning. Even advanced schedulers in the literature have not addressed aspects which are pertinent to the users and managers of these clusters, like fairness and heterogeneity well. Let's talk about some of those aspects. Companies usually buy GPUs in the thousands because it's more economic. But these GPUs are shared among various groups. One simple way to do this sharing is to create separate virtual clusters from these GPUs by statically partitioning them. However, this would make sharing of the underutilized resources hard because not all GPUs may be used by a group at all times. So we need to provide a way to share large clusters more efficiently while providing performance isolation among jobs of different users. Another phenomenon unique to DL training on GPUs is heterogeneity. Newer GPUs are released every year which are X times faster than the previous generation. Administrators create separate clusters for each generation and leave it up to the users to choose which cluster to submit to. Since everyone wants faster GPUs, older GPUs are left underutilized. Can we find a way to choose the best GPU for each job automatically? With these goals in mind, we present Gandiva Fair, the first DL scheduler to provide efficient proportional sharing of cluster-wide GPU throughput, handling of GPU heterogeneity transparently to users, and utilizing migration as a first-class primitive to achieve the above two without resorting to preemption. It's a unified scheduler where users can run their jobs on a large heterogeneous cluster of which they are provided a share. In short, one cluster scheduler to rule them all. Now, I will describe the design of the system. We make the following assumptions in our design. Users are assigned tickets. Users have the right to a number of GPUs in proportion to their tickets. So if two users have an equal number of tickets on a 100 GPU cluster, then they are entitled to a GPU throughput of 50 each. Tickets are divided equally among all the jobs of the same user. Jobs can have different GPU size requirement. For jobs which require more than one GPU, all the GPUs must be co-scheduled, also called gang scheduling. For jobs with GPU requirement larger than can fit on a single server, we must coordinate their execution across all the servers they are running on. Finally, we use the same time slicing and migration primitives used in Gandiva. Let's first take a look at stride scheduling, a ticket-based proportional fair scheduling policy. Consider this example of two jobs A and B with 4 and 1 tickets respectively. For each job, we maintain a pass value which denotes the service that job has gotten until now. In each time quantum, we schedule the job with the minimum pass value and increment its pass value by the inverse of its number of tickets. As shown in this example, A gets 4 times as much service as B. We modify stride scheduling to be gang aware. Consider this example with 5 jobs with equal number of tickets, but with different sizes running on a 4 GPU server. As before, we maintain a pass value for each job, but now we can schedule more than one job in each time quantum. We go over the jobs in the queue in the increasing order of their pass values and then schedule the jobs until all GPUs are scheduled. To be work conserving, and increment the pass values by their size divided by their ticket values. As shown in this example, all the jobs get an equal service of 4 GPUs per 5 time quantums. A question arises then, how do we use the gang-aware stride scheduler to run jobs on a cluster? Consider this cluster of 2 servers with 4 GPUs each. We could have single GPU jobs. We could have multi-GPU jobs, but which fit on a single server. And of course, we need to time slice jobs of various job sizes. And we must be able to run multi-server jobs. Well, one simple way would be to treat this cluster as one giant server with all the GPUs and run the scheduler across it. However, the central scheduler is unscalable, it becomes the bottleneck, and will result in an unbounded number of migrations across servers as jobs can be scheduled on any GPU across the entire cluster. To address these issues, we can run an independent instance of gang-aware stride on each server to schedule the jobs running on that server whose GPU size requirement fit on one server. How will we then run multi-server jobs? We introduce some central coordination. We now present the complete design of the split stride scheduler. We have a central stride scheduler to coordinate the execution of multi-server jobs, and we have a local stride scheduler running on each node. Every time quantum, the central stride scheduler decides whether to schedule a large job and informs all the local schedulers to run it, or it lets the local gang-aware stride schedulers run, in which case they pick a set of jobs from the ones running on that server and run them in that time quantum. The scheduler is fair if the load is balanced across all of the servers. You can find more details about what the load metric is and how it's balanced in our paper. Now let's take a look at how we handle heterogeneity. We start with the observation that the speedup obtained by a job on successive GPU generations is unpredictable and has a large variation. We transparently profile jobs to determine their performance and hence speedups on all GPU generations. We assume that all the jobs submitted by one user have the same performance profile, for example, as a part of a hyperparameter exploration job. We can simply then place the job on the fastest GPU subject to contention. But can we do better? We know the utility of faster GPUs is not the same for all jobs. Consider the scenario where there's a cluster of 2 V100s and 8 K80s shared equally among 2 users, U1 running super resolution with a speedup of only 1.2x and U2 running resnext with a speedup of 6x. The aggregate performance obtained by these users in terms of normalized K80s is 5.2 and 10 respectively. If we exchange U1's V100 for P of U2's K80s, both users' performance will increase if P lies between 1.2 and 6. Let's set P to 2. The performance of both users increases to 6 and 14 K80s respectively. One issue with this exchange is users could artificially slow down their jobs on K80s to win V100s. To remedy that, we introduced Vickery auction. We use the speedups as bids and the highest and the lowest speedup user as the seller and the buyer respectively, and then set P to the second highest speedup or the second highest bid. This scheme is incentive compatible. It's in the interest of all the users to report their honest speedup. Gandiva Fair is built on top of the same framework as Gandiva, but with the split stride scheduler and the automated trading policies in place. It's implemented as a custom scheduler on Kubernetes. The manager contacts the Gandiva client to perform operations like time slicing and reporting the statistics of the jobs. Talking about results, here is an evaluation of the fairness provided by Gandiva Fair on a homogeneous cluster. In this experiment, there are 70 users each with one job of 1, 2, 4, or 8 GPUs with tickets in that proportion. On the left, we can see the average GPU throughput obtained by the users of each class. The dotted line shows the ideal throughput for the users of that class. As we can see, users obtain GPU throughput close to their ideal according to their ticket distribution. This next experiment is a comparison of the aggregate performance measured by number of mini batches per second obtained by each of the 4 users with and without trading. As we can see, users 1 and 4 gain about 30% performance as compared to the baseline. Users 2 and 3 have a performance same as that of the baseline, demonstrating that using trading has improved the efficiency of the cluster without sacrificing on the fairness aspect of other users. In conclusion, Gandiva Fair is a domain-specific deep learning scheduler that provides performance isolation through efficient sharing of cluster-wide GPU throughput among users, and it allows for transparent handling of heterogeneous resources using a novel automated trading strategy. Thank you for listening to my talk.